So I wanted to just like show the image of what's happening inside the plate settlers. So remember, inside the plate settlers, we have this aggregation of particles. So the flocks aggregate as they slide down the plate. So this is what that looks like. So an animation of that piece in more detail. Um, Granted, I just said, did I say this? This is what this looks like? Like, I'm making this up. You know that, right? Like, I've never seen this. I'm imagining that this is what's happening. Okay, I just wanted to clarify. Um, although my students do like humor me and tell me that if you create an animation, then it's true. Um, that PowerPoint has an automatic physics checker in it, and you can't actually animate anything if it's not physically real. I don't know. You can check that out later and see if that's true. Okay, so you saw it happen. You saw it happen on Monroe's slides. Bunch of particles went up, they slid down, they formed an avalanche, they aggregated into a larger particle. So that was good. That's how we get our blue guys. And this is cool. I think I didn't have this insight before putting together this set of notes, that I never knew how particles that are removed by a plate settler get to the bottom of a sedimentation tank. Did I talk about this on Tuesday? I've been talking about these ideas with a bunch of people lately because I'm pretty excited about them. So this is another cool insight. Everybody has plate settlers, not everybody, but most water treatment plants have plate settlers. And we go through the design for them is actually very simple. And you're like, yeah, we designed this plate settler and the flocks get captured in the plate settler, and then they're removed from the bottom of the sedimentation tank. And they forget this one little piece, because in between the plate settler captures them and they're removed from the bottom of the sedimentation tank, you're assuming that these flocks have the ability to travel down through the sedimentation tank. And in most modern sedimentation tanks, the water is flowing up. And the reason that the flocks didn't stay in the bottom of the sedimentation tank initially is because they didn't settle fast enough to stay down. So how do they get to the bottom of the sedimentation tank ever? The only way they can ever get to the bottom of the sedimentation tank is if they gang up together and get a higher terminal velocity. So isn't that interesting? So that's what's happening inside these plate settlers. And it's been happening for decades and nobody talked about it because we didn't really think about, well, what's going on that allows these particles to get back to the bottom of the sedimentation tank? Okay, and then there's this next point. As the big flocks fall from the plate settlers, they break if they're bigger than the size set by how strong they are, their bond strength and gravity. So that's the next piece. There's a messy equation that you didn't want to see, but just to say you can do the physics and come up with an equation that describes the maximum size that a flock can grow to. And so let's look at that. Do I do that one? Yes. So the next one is that these flocks have a maximum size. So let's look at that. So we have a flock that is falling out of the plate settlers. It's a bunch of green guys that have joined together to form a big monstrous blue guy. It should actually be another color yet. It's bigger than a blue guy. And as it's falling, it's experiencing shear. And I think this is a little bit messy to think about, but think about a sphere. Forget about the fact that it's a flock for a second. It's a sphere and there's water flowing around it. And that water is shearing, is applying a force of shear to that particle. And that's all rotating, like my hands are rotating around it. So there's this moment that's being applied, trying to actually tear the flock apart. Can you see that in your mind? That the flock at the bottom is experiencing tension and it's being pulled apart and try to roll it up. So all you have to do is provide enough shear so that the one bond that's holding this flock together gets broken. And remember, this is another key idea. We have the idea that these flocks form by by rolling together I just realized that I made an assumption there that wasn't necessarily accurate. Okay, so let me step back. In the flocculator, we've learned that only similar sized particles can collide because of their boundary layers. They can't actually get close enough to touch. I don't know what happens in the plate settlers. In this avalanche, I don't know who all is combining. All I know is that there's a bunch of green guys up there and they're being rolled together and they form something that's quite a bit bigger. So the next part, we're going to have to critique a little bit. The assumption is that there's one, although you could change this assumption to say that it's a couple bonds that are actually holding the flock together at its weakest point. And so as the flock is slowly moving around, it's getting in tension at different places. And if the tension exceeds what the bonds can handle, pop, that thing opens up and we've got two flocks instead of one. And we've got to have another animation so that we can prove that this is what happens, right? So look, there it is. It happened. This flock was experiencing too much. Sorry, this flock was experiencing too much shear, causing it to experience tension at the bottom, and it opens right up. And that sets the maximum size of a flock settling on planet Earth due to the force of gravity. You can actually, here I have the equation at the bottom again for what the diameter of that flock is. You could also solve for the terminal velocity of that flock. And you know what that means? It means that there's a maximum terminal velocity for flocks that you can get as a function of what the flock is made of, like how dense its core particle is. And that maximum terminal velocity means that if you design a sedimentation tank where the upflow velocity is faster than the terminal velocity of the biggest flocks, then nothing will be in your flock filter and nothing will be able to get out of the plate settlers and down to the bottom of the sedimentation tank. And that's an interesting failure mode that should be considered. It will happen under the worst conditions, and the worst conditions are cold temperatures when things settle slower and flocks that are super low density, like organic flocks. Those are the ones that won't get to the bottom of your sedimentation tank if your upflow velocity is too high. I've got 5 minutes yet before you can give me a timeout. Okay, so let's talk about some laboratory results that we obtained. So you can actually see some of this, that it's not just an animation by Monroe, but actually some video, some real video that has been untampered. Okay, so this is some flock research that we did, and we were trying to figure out what's going on inside of our sedimentation tanks. And so what we did is we looked at our sedimentation tanks and we realized if we could take one little slice of a sedimentation tank from Honduras, that's half the width of a sedimentation tank. And if we could take that slice and bring it into the lab, so there it goes, 2,000 miles from Honduras to the lab. And then if we make it not 6 meters long like we do in Honduras, but we'd make it half an inch, sorry, switch to metric, 1.25 centimeters. And now we have this thin little sedimentation tank slice, and we can make it out of glass and we can shine light through it and we can actually see what's happening as flocks move through that. So there it is. This system has a flocculator, and you should chuckle to yourself and say, Monroe, you didn't teach us how to design these flocculators. They're just a bunch of tubes wrapped around some cardboard, I don't know, pipes, tubes. And this is a laminar flow tube flocculator that works for really low flow rates. Doesn't make sense for municipal plants, but it works in the lab. And then there's the flock filter part of this unit, and there's the tube settlers, which are like plate settlers, except they're round instead of rectangular geometry. And there's no filter in this system. And now we run this, and let's see if this works. Okay, so this is video that was taken by my PhD student, now Dr. Casey Garland. And remember, she's shining light through it, and we're going to see what happens as a function of time. So here it goes. And hang on, let me pause this so I can talk a second. Okay, so on this graph, the blue line is the turbidity, or she's reported it in milligrams per liter coming out of the top of the tube settlers. So that's the clean settled water. The green line is a spot up here near the top of the flock blanket, above the flock blanket. It's a supernatant coming off the top of the flock blanket. And this is great. Look at that. Look at that green line. It's like, I don't know, 300 or something, or 250, and it's constant the whole time. It never changes. I wonder why that never changes and why it's so high. And actually, Casey would jump in here and she would say, and it happens to be equal to the concentration coming out of the flocculator. Oh man, I'm going to stop right there and go back to this previous slide if I can. Hang on, I got to figure out PowerPoint tricks. So there's red and green coming out of the flocculator in the very bottom, this inlet manifold that's down here at the bottom. What happens to all the red and the green flocks? What happens to them as they go through the flock filter? Who gets left behind? Anyone? Who gets left behind in the flock filter of the red and green? A couple of the red ones. They burrow into a blue one and are captured. But all the other ones go right through. And so the concentration up here where Casey was measuring it is all the green ones and still some of the red ones. And because the vast majority of the flocks, or the particles coming out of the flocculator, are green ones, they're already flocculated, the turbidity basically doesn't change. So all of the particles that came out of the flocculator are actually at the top of the flock filter too, minus a few red ones.